Swayam Prabha. Digital India. Educated India.
Welcome to the class of high performance computing for scientists and engineers, and we are discussing about fundamentals of parallel computing, which is the first module of this class. Till now we have discussed about architectures of parallel systems like shared memory and distributed memory platforms. We discussed about parallel computing architecture models, different models of parallel programming, how to design a parallel programming, and we have seen that in a parallel computing infrastructure there are some limitations in the sense we really cannot get a linear scalability, and we will discuss about scalability in the next lecture, in that sense that if we have a problem which is taking 5 hours in a sequential program or a single processor, if we use 10 processors it will not take 0.5 hours or 30 minutes, it will take more time than that. So, it is a parallel system is not an ideal system. If we increase more processors, we will see some enhancement in performance. However, the performance enhancement is not exactly as the time divided by number of processors. That means there is some overheads, and we have discussed in detail about the overheads in shared memory and in distributed memory machines. One part of the overhead is due to communication, the time required by communication across the processors. There is also overhead due to synchronization. If we see the shared memory machine, communication overhead is mainly due to the sharing of similar data in same data in different processors, where their caches have to be coherently updated, and therefore some amount of time will be gone for this cache coherency protocol. There will be false sharing, which again is due to this cache coherency protocol itself. There will be race condition, the same data is being trying to operated by different processors at the same point of time, like that. So, this is a shared memory machine. In a distributed memory machine, data has to go from one processor's memory to another processor's memory using a network switch type of thing, and that will require certain amount of time. And then when there will be synchronization across different processors, that at some point of time all the processors have to wait till one has finished their work. We will see there are some synchronization like critical or atomic in case of shared memory machine, where one part of job, though it is inside a parallel loop, is operated sequentially by different processors. And in any parallel program there are some operations which cannot be done in parallel, which is inherently serial or sequential, like it has to read from a file. Even if all the processors are reading from the file, it is the same job everybody is doing. So, there is no parallelism in that. So, therefore, these things will add into the overhead of especially communication synchronization overhead of the parallel program, and this overhead will depend on the algorithm, on the program, the problem that we are trying to solve, as well as on the hardware and compiler, which the parallel programmer has least control. It is what is given to him. And there is another overhead which is called a load balancing overhead, that is or a latency, that is that not equal amount of task is given to all the processors. So, some processors has finished their task earlier, some are still waiting, and therefore, the waiting processors are gone into an idle stage, though they are in operation, though electricity is passing through these processors and they are very much counted to be operational, but we are not getting any benefit of their computation at that particular time when they are idle. And naturally, in any computer's CPU cycle has some idle time also. So, this some idleness is due to load balancing, some idleness is due to the hardware as well as the operating system processor scheduler itself. So, these overheads are there, and due to these overheads, even if we are increasing number of processors, we may not get the best desired output. So, it is important to know what is the best output possible out of infrastructure. Can we increase that output in some way? If we are not getting that output, what are we doing wrong? If we are trying to do something, we are increasing number of processors, but we see that we will not get any benefit in terms of computational time or in terms of computational cost. What can be these situations? So, it becomes important to look into performance metrics of parallel systems. So, which is this particular lecture is about, that what are the performance metrics of parallel systems. We will discuss about performance metrics, that means what are the terms by which we can quantify performance of a parallel system, and this performance includes this performance is the overall performance of the system. It includes the performance of the hardware, performance of the computer and other software support, as well as the performance of the program, of the algorithm and the program. Some part of this we can control as a programmer, as a person working on the algorithm, we can improve the performance, but beyond a limit we cannot improve the performance, because it should be limited by the hardware and the other backend softwares. What are the overheads and what is efficiency of a parallel computing system? So, how I can if we are using a problem in two different architecture, one is having 10 processors, another is having 80 processors. How we can see that which one in which case if we are using it more efficiently, which what is the issues? Because you see, when we are using more number of processors, we have to spend more money in terms of electricity maintenance. We have discussed earlier, as the processors are working there, their CPUs and chips are being heated on, and they require electricity. Further, to dissipate this heat, we require certain amount of cooling, which also require power or electricity. So, even if we are increasing processor, we are getting some betterment in time, the computational time is reducing, but it is it being done in an efficient way? And then we will see what is the maximum limit of performance of a parallel program or a parallel computing infrastructure, as well as a parallel program, and that is called Amdahl's law, which gives a cutoff that this is the maximum efficiency, or this is the maximum best performance you can get out of a parallel program, depending on the program, the algorithm itself, as well as it we will see, as well as depends on the programmer's effort, etc. So, first important thing is overhead in a parallel program. We have discussed about overhead in several times in this discussion. So, overheads are always obtained in parallel programs. We already know that in any parallel program there will be overhead. These overheads add over the computing time and thereby degrade the performance. So, what is the time in which the processors are crunching numbers, or doing arithmetic and logical operations? Apart from that, due to this overhead, there is some time in which is included in the total time required by the job, parallel job, and therefore, the total time will increase because the overhead time is included into that. So, the sources of overhead are interprocessor interaction, discussed about it. Processors write data to a common memory space. In case of shared memory, there will be contention, false sharing, establishing cache coherency, etc., which will require some amount of time and add to some overhead. Interprocessor communication through network switches. In case of a non-uniform memory access shared memory, or NUMA shared memory machine, or distributed memory machines, communication time depends on the distance between the nodes at the network, and if there are P processors, the communication time in a network, the communication time will be of the order of log P with the base of 2, and this can be shown through very easy calculations. I am not doing it here. And so, but we will take the fact that if there are P processors, the communication time will be log P with a base 2. Idling. Due to non-uniform load balancing, some processor may stay idle when others are in operation. Also, idling during communication, blocking communication, that means one processor is communicating to other, while communicating it is blocked, it cannot do anything else. So, and when the other processor is receiving, when it knows that the other one is giving some data to it, while receiving it cannot do anything. At this time when the communication is being done, the processors go into an idle stage, they do not compute anything though they are in operation, and there are some plus minus times during communication when which they also go into idle stage, as well as when there is a synchronization, that all the processors have to wait till all the other processors have finished a part of the comes up to one part of the job. So, when this synchronization is given, or for shared memory programs, some part of the memory is accessed sequentially by all the processors. We will see atomic or critical commands when we will do OpenMP. So, these are called synchronization steps in which processors wait for the other processors to finish up to some work, and then they go into idle stage. So, when they are idle, though they are operational, though they are adding to total computing time, but they are not doing anything, basically they are in idle. So, they are adding to overhead. So, these are the main two sources of overhead. One is interprocessor communication time, interprocessor communication and idle time, and we have to, and the third overhead is excess computation. So, excess computing steps are associated with parallel version of the algorithm. If we take the sequential program, the serial program, there is some computing steps, but when we think about a parallel computing, we can understand that we have to find out that how many tasks are there, do some task interaction type, task dependency type of graphs, which task will go to which processor, this mapping has to be done. Once the processors have done their work, we have to take their output and combine them or write them into a file, or do something with that output, do a operation over different outputs coming from different processors probably. So, some computing will be added over the serial program when we think about a parallel program. So, this excess computing will be added, and this is the third source of overhead, will be added to the sequential program. So, these three was not present when you are thinking about a serial program, but when you have thought about a parallel program, these three extra time, one is due to interprocessor interaction, another is due to idling due to communication or synchronization or non-uniform load balancing, and excess computation are added to it, and therefore, they will degrade the performance of the system. And now, we will see that how do they behave in certain cases. So, this is a figure taken from Gramagupta Karipis Kumar book, that execution profile of a hypothetical parallel program. Say a parallel program is running over 8 processors, and when they are running, we try to find out that over a certain amount of time which processor is doing what thing. The black one is the computation, and this can be the essential communication, which was essentially present even in the serial algorithm, or the excess computation added due to our parallelization of the job. The grey one is the interprocessor communication, and the white one is the idle time. We can see that in any of the processor, it is not only computation. Computation is some part of time, but at least 10 to 20% time is gone for idleness, as well as, so these are the idle times in one processor, as well as interprocessor communication. Therefore, if we add up the total time of used by all the processor, a substantial amount of time, which is in between 10 to 20% of the total time, is gone for something which is due to interprocessor communication and idling. And we can understand that as we are increasing number of processors, we should get faster solution, because many computers are taking care of the large problem, and it will be solved faster. But the interprocessor communication has also increased, and probably idling has also been increased due to non-uniform load balancing. As we are increasing more processors, the load balancing becomes more difficult, and therefore, these overheads have also increased. Well, so let us look into it detail. Now, we know that overheads are there, it will always not give us the right, the most desired result. What should be our desired result? For that, or if we take two different parallel systems, or if I take a single problem, ask two different programmers to make two parallel versions, So, and there are overheads. So, this performance, the performance of the versions will be probably different if they parallelize it differently. Which one is best? So, we need some quantitative figure, quantitative number, some quantitative parameter to identify the performance of a parallel process or parallel program, as well as how one particular parallel program behaves in different infrastructure. We have some homegrown cluster here, and we have a multi-core machine in which the program works better. So, to understand that, we need to find out some parameter which can be quantifiable, some quantitative estimate is required, and this is obtained through performance metrics. The first one we understand is execution time, which is denoted as T subscript P, that how much time the parallel program is taking. If you are running a program in 10 processors in one particular infrastructure, what is the time taken? And this is to be compared with the serial program's time, that what is T underscore S, that if we do not use a parallel program, what for the serial program for the same problem, what should be the time taken. However, and execution time and the speed of the parallel program, because when we think about parallelism better performance, we think that the computation will be done in a faster time. So, something like speed is important, speed is inverse of execution time. In some cases, we can also say that in one particular 1 second how many iterations or how much computation has been done, that is also a measurement of speed. But usually if we have to find out the total execution time of the parallel program, and inverse of that gives us the speed. And speed up or scalability, which is the most important, one of the most important parameter in parallel program, is the comparison of parallel speed with the speed of the best performing serial program. What is the best performing serial program? That do not take the parallel program and run it in single processor. Think that you do not have to parallelize it. Take the main problem, and what is the best possible program that can be written to solve that problem. That program, that algorithm may not be the good one in terms of parallelization, but what is that? So, take how much time it is taking. So, consider you have given a problem, what is the least time in which this problem can be solved in a sequential program, in a single processor, and inverse of that will give you the sequential speed. If you compare parallel speed with the sequential speed, you will get speed up or scalability. This is obtained by dividing speed of parallel program by fastest sequential program for the same problem. It may not be the same program running in the same single processor, because when you make a parallel program, there are many excess computational steps also, but in the simple sequential program these are not there. Also a problem can be solved in many ways, but you think of that one which gives you the fastest solution in a single processor, and that speed, use that speed to divide the speed of the parallel program. This ratio is called the speed up. That is, what is your benefit when you are using a parallel infrastructure, by which ratio you have speeded up the program. So, this is given by speed up is denoted as S, which is Ts by Tp, the time taken by the sequential program, best performing sequential program, divided by the time taken by the parallel program. Time taken by best performing sequential program divided by the time taken by the parallel program. Ts by Tp, this is given as speed up, and we can understand this is always greater than 1. If it is less than 1, I mean desired is always greater than 1. If it is less than 1 then or 1, then there is no meaning of using parallel infrastructure. The parallel program is taking more time than sequential program, and nobody will allow you to run the program in parallel. And if we draw speed up a curve for any general parallel program you consider, and you see how the speed up is increasing with number of processors. In the ideal case, that you are adding one processor more and you are getting the similar ratio of speed up. It should follow a 45-degree line. In a real case, this deviates from that 45-degree slope line due to the overheads. As we increase number of processors, speed up is increasing, we are getting faster solution. However, it is not as fast as the number of processors are being added, because with increasing in processors, the overheads are increasing, and we understand that overhead depends on interprocessor communication. We have earlier seen interprocessor communication time is of the order of log p to the with a base 2 log. So, as we are increasing number of processors, interprocessor communication time or overhead is increasing, as well as synchronization overhead and load imbalance overhead, all these things will add. So, this will the actual speed of curve will deviate from the 45° slope line, and eventually it might come to a maximum, and then it starts showing some reduction, so showing a it will start to show reduction, and it will reduce, the value of speed up will reduce with increasing number of processors. If we use a very large number of processors, at that point of time it is not meaningful to use a large number of processors. We have to, so when it is reaching a maximum, we will probably stop, we cannot add any more processors, that is not beneficial. And it is also our desire that this curve should be much close. So, it is also one of the desire that this curve should be much close to the actual curve, to the ideal curve, that the overhead will be less and we will get better speed. What does it mean? That if we consider another curve like this, it means that with as we are increasing the number of processors, the speed is increasing more than the curve shown here. So, that is a much more acceptable parallel program. Now, what is the best possible parallel program? Okay, 45° is the linear scalability. There are some cases when you get superlinearity. So, the curve actually shows more, the curve actually goes like this, but we are not discussing it here. It has more complex issues involving hardware and memory access, but our desire will be the curve should be pushed more towards this line, that the overhead will be reduced. So, what is the maximum limit through which we can push that? That is also you need to know, because if we have already reached the maximum limit, we should not spend more time to increase the performance. It is like trying to violate laws of thermodynamics. If you have already reached Carnot efficiency, you should never think of increasing the efficiency. Similarly, so one term called efficiency comes here, and what is efficiency? Okay, the overhead is due to I have discussed it, non-uniform load balancing, communication unsynchronization overhead, and excess computation we have discussed. So, efficiency is speed up divided by number of processors. So, ideally efficiency the efficiency of the 45° slope curve is 1. I have discussed about superlinear speed up, let us forget that at this stage. So, the ideal efficiency is 1, but can we reach efficiency 1? We have to see, and this is therefore given as efficiency is equal to S by P or Ts by PTP, the sequential serial programs time divided by parallel program time into the number of processors. And here comes another thing, efficiency. We know that efficiency is as I discussed comes from a thermodynamic discussion, that how much we are cost we are getting, how much benefit we are getting compared to how much cost we are spending, how much energy we are getting compared to how much energy we are spending. So, this is the Ts is the serial program time, single processor program time. This is the job it is being done, is getting done, and this is what we are spending in terms of our parallel infrastructure. What is this PTP? Well, I will come to PTP, but a scalable system is called a system with nearly constant efficiency. We will discuss about PTP later, this is also important. Nearly constant efficiency means if the efficiency remains constant, if we increase the processor, say if E is constant, if we increase the processor by 2, TP will be reduced by half. So, as much as we will by a factor of 2, TP will be reduced by half. As much as we will increase the processor, we will see the same effect in the speed. The speed will be increased similarly, and that is called a constant efficiency system or a scalable system. This it is very desired to get a scalable system. If you have a scalable system, you just increase number of processors, you get in the same ratio, you will get your speed up. of computing. So, you can predict what will be the computational time just by increasing number of processors. There has to be something with the overhead also, and we need to see that. Yes. And what is overhead? Difference between serial time for fastest serial algorithm and parallel time multiplied by the number of processors is called the total parallel overhead, and we can understand that TP is the time taken by the parallel program, and there are P nodes there. So, PTP is the total time spent by all the parallel processors for that program. And what is its difference from TS? It is of course greater than TS because of communication and other overheads are including there, and this difference is simply called the overhead, PTP minus TS. Sorry. Overhead increases as number of processors increase. We can clearly see it from here that because efficiency is not 1, therefore, PTP is always greater than TS, and as we are increasing P, the overheads will increase, and that is the behavior of the system also. The increase is usually non-linear with increasing rate. As we are increasing the number of processors, the overhead is increasing, and this increase of overhead is increasing with increasing number of processors. As we are increasing number of processors, the overhead is increasing more than in a linear rate. The rate is also increasing. It is increasing more because computational overhead, communication overhead is for P number of processors is given as log2 P. So, it is the rate is also increasing. As we are increasing processor, it is not linearly increasing, it is super linearly increasing. The term PTP, and I said this is important, this is the total time spent by the processors in solving the problem. TP is the time spent for solving the problem in a parallel environment, P processors are there, therefore, combining all the processors is taking PTP time. And what is happening in this PTP time? And this is known as cost. In this PTP time, all my processors are on, they are taking electricity, they are taking AC power, etc. They are taking all the operational cost, the capital cost, everything is included. In true sense, this is the cost of running HPC system and energy requirement. So, while getting parallel performance, many measures are important, and we will discuss about different other measures, but it is also important that we should be aware of this term PTP, which is the cost of running a HPC system for that particular problem. And as we are increasing overhead, PTP will increase, cost will be more. So, we have to reduce overhead in some sense to get better PTP. Thank you.